people wait till the end, or I have no problem.
As you want, yes. I suggest to people to write it on the chat, and then you can answer them as you feel, or at the end, or in small stops on the middle.
Okay. Yeah, I have chat window. It's very small one, but
maybe after 15 minutes, make a small stop, see what questions are, and
all right.
Something like that.
Does it have option raise the hand? Because no, I don't see it. You don't have an option raise the hand.
Let me check on the meeting options.
Anyways,
just write on the chat.
Let's go ahead.
Write on the chat. Yeah.
Yes. If you have any questions, guys, feel free to interrupt and post your questions in the chat, and I pause, and we'll try to answer any questions. I have around 40 slides, and probably a bit more than 40. I'm sure we won't have enough time to go through all of this, and I kind of will try to pause and focus on most relevant for you. So first, thank you for introduction. I am Pavel Shames. I work for ARM Research. Specifically, my focus of my research is high-performance interconnects in co-design, interconnect, hardware, and software layers. And I will start with going over the project and describing essentially how we started the effort. UCX, which stands for Unified Communication X, is part of UCF organization, which helps us to manage this project and a few other projects. There is multiple members in these organizations. We have board of members as well. On board, we have people from Salamos, AMD, NVIDIA, IBM, ARM, Mellanox, Ohio State. We also have multiple third-party contributors that contribute to the project. Under UCF, we manage multiple projects. So the ones that I will be covering today is UCX, Unified Communication X. And there is a link to the website. We have a few more projects like Spark UCX, which essentially implements Spark on top of UCX API. We have OpenRDMA that focus on RDMA interfaces. OpenSnappy, which focuses on smart NIC APIs. And most recent project is called UCC, which is collective library that will be focusing the implementation accelerated collectives for MPI and ML and AI frameworks. So we started UCX when I used to work at Oak Ridge National Laboratory. We started back in the day a small research project was called UCCS, with the focus to develop highly accelerated point-to-point layer for biggest programming models, specifically OpenSHMEM. And the idea was, hey, since a lot of semantics between OpenSHMEM, PIGAS, and MPI, to some extent very similar, both frameworks, all the frameworks trying to send messages or using one-sided messages. Let's try unify all these communication properties in one library and have one library that will provide services to MPI, OpenSHMEM, and potentially other emerging programming models out there. And at some point, we realized that other organizations, commercial organizations like Mellanox, IBM, already have some work in this space, and hey, it will be better to try to collaborate and work on this together. And it really, project started very, very small. We had 4 people in the room talking about, what they really want to achieve. One of our interns started work design on logo for the project, and the doodles with few guys on the side here. It actually was first logo designed by our intern, and at the bottom you can see our first face-to-face when the project started to grow, not just 4 of us, but few more people joined us. This is a meeting in basement office of University Tennessee, Knoxville, with George Basilica and people from Jack Dangara group and so on. And this is, pretty much all we had. We posted this page with pen written UCX on it on the wall there to announce that we have this meeting and so on. So it started really, really small. It's just few researchers have an idea. And along the years, like now we almost over 6 years, I would say 7 years into the project, we have many more people involved in this. In last release, we had over around 30 contributors to the project, and most of the out of 30 contributors, most of these people are full-time engineers working on the project. We had multiple face-to-face meetings in Austin, Texas. We had one at UTK and so on, multiple participants. So it is much, it grew up from very small project to substantial size project where you have multiple companies involved. We have now multiple commercial products built on top of this. Companies like Mellanox, NVIDIA, IBM, Huawei, and others actually provide UCX as their product and part of their software distributions with their software stacks and so on. Last year, another highlight for the project from the last year, we were awarded R&D 100 award. This is quite prestigious award that awarded once in a year to 100 projects in various domains, and materials, science, chemistry, energy, you name it. There is a segment for software engineering and high-performance computing, and we received this award as part of this group. We were proud of this. It's nice poster that was designed by a graphic designer from, I think, Los Alamos National Laboratory, describing our vision that we started UCX, something that powers and runs on supercomputers, but we also built it with the goal to run on embedded devices, on smaller devices, not just supercomputers, SmartNICs, and so on. And we see slowly we see that our vision comes to life with all of this. And UCX is a highly portable library. It supports x86, AMD and Intel, Power 8, 9, ARM v8. We have microarchitecture code inside of library optimized for Xeon, AMD ROM, ARM, various ARM implementation, support for AMD and NVIDIA GPUs. And it runs on broad variety of hardware. And when I joined ARM, one of my first development platform was its Raspberry Pi. It's what we have there sitting on Android C2, which is sort of different variant with similar idea. It's a bit more powerful than Raspberry Pi on my Mac, and it's where I started porting of UCX to ARM. You have Thunder X2, you have NVIDIA Jetson where we're running UCX. It's running on Bluefield. On right bottom, it's N1 SDP. It's most recent platform for ARM. I mostly use pictures of ARM machines here because I work for ARM, but obviously it runs on many other platforms besides ARM. This is a high-level architecture of UCX, and I will go a bit more in details on this slide. So what you see in the red border in blue, it is library is a part of UCX. So UCX is project, it's framework, we call framework, because when you build UCX, it actually creates multiple libraries that eventually APIs and others use. UCX exposes three interfaces. We have C API, and this API used by MPI implementations and other, C-based HPC projects. Most popular one is MPICH, OpenMPI, OpenSHMEM. Actually, MPICH today, if you download MPICH code, it's already embedded inside UCX code. They made it part of MPICH distribution. OpenMPI, for OpenMPI, you have to install UCX separately. OpenSHMEM, there's multiple implementation, depends which one you use. Again, you can get embedded on separate UCX build. We also have Java APIs that are used by Spark UCX, and quite a few proprietary libraries that recently people started to release in this space. We see that seems like most of our Java users coming from data analytics domains, like Spark, like data distributed databases, and so on. And we also have UCX Pi, which is, as for now, it's really not part of UCX distribution. It sits in separate repository. It's developed by group of developers from Rapids project. It's separate now because they want to make really fast progress and not to go yet through our review process. So it sits on the side, but it's already today used by multiple AI frameworks, and Rapids AI and Dust probably one of the most popular ones. And we, through UCX Pi, we have quite a lot of Python users. It's very simple API. It's nicely integrated with Python 3. You can use Python 3 features and so on. So very easy to use. With all the three APIs, what they expose what we call UCP API. We have libucp. This is our top-level API. This is somewhat high-level APIs that expose send-receive semantics with MPI tag matching, semantics similar to MPI tag matching. We have also support for a variety of one-sided operation like remote put and get, support for atomic operations, support for task-based domains, which is essentially it's active message APIs that are used by storage workloads and upcoming programming models that don't really use send-receive semantics, and something like active message maps better to their semantics. And I mentioned earlier we have stream API, it's for storage. And with UCP API, if you do send-receive, you just pass to the function buffer and an endpoint that you want to communicate to, and it automatically selects the best available transport on the system. If it's InfiniBand or shared memory, it checks where the remote endpoint is located. It checks what the source memory, what is the destination memory. It checks how many devices they have on the machine. Based on this, it decides if it has to fragment message, what size of fragment, if it has to strip message across multiple devices, does it have to use shared memory, does it have to use GPU direct to send the messages directly from GPU memory to host memory. All this complex logic is hidden inside of UCP layer, and neither MPI or programmers that work on top of UCP, they don't have to deal with any of these decisions. We sort of automate all of this and abstract it from them. UCP layer is implemented on top of our internal library called UCT. We install this API as well. We don't really have right now direct users for this API. It's somewhat low level, but essentially we call it transport layer. The transport layer is integrated with multiple different interconnects, like RDMA interconnects, which we support through RDMA verbs, and we support multiple transport like reliable connected, unreliable, dynamically connected. We also have new transport, which is not on the diagram here, but we called it MLX5, that it's highly optimized layer for Mellanox interconnects. These layers don't really use words directly. It's they directly write to the hardware all of the requests and the passwords. And this is how we achieve really high performance in injection numbers and very low latency because we bypass multiple other software layers and directly use hardware. We also have Gemini layer, which is for Gemini in areas. Is this something I developed back in the days when I worked with Oak Ridge? It was used on machines, on Cray machines that we had at Oak Ridge. Right now, we still have it installed, but I would say it's not actively maintained. Part of the reason that this API is deprecated by Cray, they are moving to different API. We have support for multiple shared memory devices, Sys5, POSIX, KNM, CMA, XPMM, this all kind of shared memory transport that's supported in Linux. We have separate transport for GPU, which is enable communication from GPU to GPU, including local or remote GPU. And we support ROCm API for AMD and CUDA for NVIDIA. We have support for TCP over sockets, Ethernet. And UCP layer essentially can take any message and split and send it over one of these transport or multiple transport, or combine this transport together for more complex send patterns. We have services in UCM layer, which is memory layer, which people don't really expose to this directly with our internal layers. They hide, again, some of the complexity from user, for example, memory registration and memory caches and memory detection, what kind of memory is used, is detected through UCM memory and memory hooks. This is library UCM installs. And integrate at the bottom, you see all the drivers or directly hardware that we use to run on. On the top, probably you guys will be using the API for your competition, and API directly interacts with interface with UCP. On top of API, you will run all kinds of applications. I'm ready to pause for questions because it's quite complex slides. Any questions so far? Okay, no questions. I will go to the next slide. Okay. Sorry. Useful links. If you go and get UCX code, it's found on GitHub under OpenUCX project. You will see multiple projects and the ones you're looking for at UCX. We have also a website, OpenUCX.com, that has pointers to like tarbles to download. If you're interested to participate in the project, you have to sign a contributor agreement, which is pretty much signing off the 3 license. It's quite typical for some of the open source projects. If you're looking for documentation, we have Wiki on GitHub, and we have more user-oriented documentation. GitHub, we keep kind of more developers focused. User-oriented documentation can be found on Read the Docs, and you have links here. We also have a mailing list that you have to go, you can register on, subscribe, and post any of your questions. And quite often, you know, when people have questions, they will go and use the mailing list, or they go to GitHub OpenUCX project and just open in the issue for us. And typically one of the developers will jump on and will answer on the question. I put some pictures of, you know, the group of people and developers that work on it. The very friendly community, very nice people. So if you have any questions, don't hesitate to ask, because there's no silly questions. Don't be shy. many of us started, pretty much many developers started from scratch on the project and probably had the same questions. And some of this hopefully already answered on mailing list. If not, we will try to help you. And to kind of improve the process, I created a new type of issues. So I don't know if you're familiar on GitHub, under issues tab, and you create an issue, it will open template. In template, I created separate label for you, student cluster competition. And we know, with this label, we know that, it's urgent request coming from you guys that, working on the cluster, trying to get your application run as fast as possible. And on the meeting today with our developers, I will know if they will see questions labeled student cluster competition. We will give priority to these questions. Next slide. Okay. More useful information. I mentioned devices, the transport, and all this information. The names for devices, transport that we use a bit cryptic. There is utility that comes with UCX called UCX info. You can, this H will report you all the flags. But there is flags like called -D, which will report list of devices and transport that UCX finds on your machine. There is separate flag to report, I don't remember it right now, to report all the tuning parameters that you use to pass to UCX. And it's great utility to learn what tunings you have, and great utility to have to dump all the list of, what hardware UCX detected and what UCT transport can be used to work with the hardware. In some cases, we have more than one. As I mentioned earlier, typically, we're trying to make all the decisions for developers, so you don't have to deal with this. Nevertheless, in some cases, when you have very exotic system that's kind of puzzling topologies, it might be useful to pass some of these parameters. I listed some examples like UCX TLS to put one useful parameter. You can list names of transport explicitly that you want to use on this machine. Here is an example at the bottom from Summit and Sierra. DC-X, dynamically connected X states for accelerated, and list of few CUDA transport, CUDA copy, CUDA interprocess, IPC, and GDR copy for CUDA as well. We have separate variables for network devices, shared memory devices, and accelerators. I showed some example how to select rendezvous scheme. We have put and get zero copy schemes. You have control over number of rails that you have when you have multiple devices, essentially how many devices used to communicate, control these rails. And popular one, it's rendezvous thresholds. You can switch between eager rendezvous projects using this variable. There is many more. Hopefully you don't have to use any of this. I think most often we see people ending up touching these parameters when they work with systems with GPUs or multiple GPUs, when they have to explicitly to enforce some of the communications through the GPU. There is also a utility called UCX pair test, which is provides ping-pong latency, bandwidth, injection rate, benchmarks. And I think this is the first step to check if your UCX library operates correctly. You can essentially run separate benchmarks, look at basic latency, and if you see that, for example, latency numbers, bandwidth numbers is off, you have to go and adjust your tuning or start the debug. I see Ophir posting other useful flags for UCX info, like -C and -F. Thank Kefir for doing this. C dump securing defaults, and F shows all possible configurations. We have, so I mentioned earlier, we have rapid read the docs site. So we have for more tunings, explicit examples on read the docs and on Git and Wiki. Actually, it's kind of similar. How to build OpenUCX and MPitch with UCX library. I will add that if you operate on InfiniBand cluster, we provide with GPU or without GPUs, we definitely provide best-in-class performance on market today. So if you want to have, best bandwidth, best injection rate, lowest latency, with InfiniBand cluster, GPU cluster, without GPU cluster, or cluster with NVIDIA GPUs as well, I would strongly advise to use UCX. We provide great shared memory performance as well. I believe it's probably in some of the best on markets. I think it's the best. For TCP and Ethernet, we also provide great performance. It's still ongoing tuning work. I saw some recent comparison. I think it's very comparable to implement other TCP implementations that comes with OpenUCX and MPitch. It's rather comparable to what you have with other implementations. So I will highlight some of the recent releases and development on the project. So 1.7 and not the most recent release, but anyways, I will go and highlight some of the features that we have there. UCX exposes server-client semantics, so we have support for now for servers listening on multiple transports. We have now connection manager running over TCP transport. Multiple improvements around essentially server-client semantics, which is actually mostly used by ML and AI workloads. We see less users in MPI for server cluster. Active message, again, this comes from other programming domains, was added in 1.7. We added better support for deal open, which is for MPI, and means that it's better support for registration cache. When you run MPI with large messages, UCP now will try to intercept and use our registration cache to optimize your rendezvous communication or GPU communication as well. We have now support for PCI atomics, which means if you run atomics, it will have better performance compared to software-based atomics. Support for Java API, Mellanox DevX API, it's what they called highly optimized layers inside of UCX for Mellanox devices. It was updated. So again, it's very important to go and make sure that you use latest grades of the UCX version. Multiple optimizations for TCP. We also optimize our memcopy implementation for Intel platforms. Quite often inside of UCX, you have some messages going through bounds buffers, also shared memory. So we have our implementation of memcopies that are based on microarchitecture properties, which is highly tuned for networking. This most recent release that we are releasing April 1.8, link to this release. This is the latest one. It's one you want to use. Again, multiple improvements for Mellanox devices, improved scalability for TCP. We have tons of improvements for ROCm, which is AMD's interface for NVIDIA GPUs. So that was improvements in benchmark, support for tag matching when you work with ROCm with AMD GPUs, and so on. So this really where we have probably brought up support for AMD GPUs up to speed and now compared to what we have with CUDA. Improvements in shared memory like XPMEM, support for strided receive when you have data types, which is not contiguous memory but strided. Support for containers, I will mention later on. UCX used on Azure, it's used in other cloud environments like Valve and so on. So there is multiple improvements for cloud-based systems. And this is first preview of release of UCX Java, which now available through Maven central distribution. If you program Java, it's very convenient. We have now almost all APIs available for Java as well. In 2020, some other updates. So UCX Pi, if you're into Python development, there's a link to GitHub of the UCX Pi distribution. I think that you can install through condos and multiple channels. It's installed with Rapids and so on. I think there's containers that comes with UCX Pi as well. Yeah, go and give it a try. It's very nice, very easy, very Python friendly. I mentioned Java. We had first release. We have Spark UCX, which is Shuffle plugin for Spark, available on GitHub as well. If you run Spark, it's very useful. We have new upcoming projects that last week we had virtual face-to-face meeting for a couple of days. This new very exciting project that we have multiple companies participating. I shared here codes of research projects. This is effort based on one from University of Jerusalem and Valve, another one from Mellanox. Which provides their implementations, actually publish papers and already advertised numbers with these layers. And now they essentially work on new projects that converge these two code bases in the single code base that will have all the features from each one of the projects. And this API targets, first of all, MPI. It will have hardware accelerated APIs and ML and AI workloads that, for example, will enable communication, something like with collectives through Nickel and so on. There's actually ongoing work, at least here with UCX and Nickel integration. We have new API for active messages that was driven by IBM. FreeBSD macOS not supported yet, but it's work in progress. For now, we support only Linux, various distribution of Linux. FreeBSD is ongoing work. Hopefully this year we will finish the porting. And we have new read the docs documentation. It's a great resource for learning about UCX. And if you don't find answers there, please ask on GitHub, send us emails and so on. So I finished kind of this overview of the project, and the next slide is more of me kind of sharing slides from our other contributors to the project, what work they doing with UCX. So I pause here and provide opportunity again to ask any questions before I will jump into presenting a sort of overview of other efforts using UCX. Any questions? Make sure that you unmute yourself if you have questions. Okay, I will continue. So picture here is again, this is from ARM. I will present some R examples of UCX using in deployment. This is Astra supercomputing system deployed in Sandia National Laboratory. I borrowed the slide from Michael Aguilar from Sandia. It's first petascale ARM system based on Thunder X2, which is ARM. It's server CPU developed by Marvell. It's based on ARM v8 architecture. And this APIs that user at UCX to run the system, and this was APIs that was used to get the top 500 runs from the system and so on. And it's the same implementation that we use for x86 and Power used to run on ARM system, and this kind of highlights portability of library across various CPU architectures. There's some numbers that I run on our internal development platform with ConnectX 6 from InfiniBand card from Mellanox is 2 by 200 gigabit. This is software development platform, essentially it's test chips that I'm running on with InfiniBand, PCI Gen 4. You see with transport layer, we get sub-micro latency with UCT over InfiniBand, just slightly over 700 nanoseconds, and with single core. Ping-pong latency back-to-back no switch, we get over 16 million messages per second. With UCX, if you use verbs with post list, which post list of messages, we get up to 32 million messages per second. And these are very, very nice performance numbers that pretty much demonstrate that, with ARM and Mellanox, InfiniBand, ConnectX 6, you can pretty much achieve state-of-the-art some of the lowest latency and high-speed injection-based rate numbers. This slide I borrowed from Steve Poole, Los Alamos National Laboratory. So Los Alamos, they're working on SmartNICs, and they have deployment of a system where they have a mix of hosts, and the hosts they use Mellanox Bluefield, and the UCX they used to run on Bluefield on the SmartNIC and on the host itself. So on SmartNIC you have on Bluefield, I think it's between 8 to 16 ARM cores, and on the host you have x86 cores, and you can run on both. You can run application on the host itself and SmartNICs that sits inside of the host. So they run some OpenSHMEM-based workloads that distribute the application across hosts, and this very capable SmartNICs, and they demonstrated some results and performance and so on. I believe if you Google for this title, the poster, you'll find it online. This slide I borrowed from Ken and Pawan from Aragon. They use UCX for MPH for InfiniBand systems. The benefits, obviously, is a very lightweight library with very low latency, high bandwidth, and it provides all the greatest latest hardware acceleration to MPH, so they benefit from all this performance acceleration capabilities. They also have support for accelerated verbs and GPUs, and this is something that MPH leverages exposed to their users. And there's some numbers that they shared with accelerated work, for example, showing, I think it's message rate, shows that by using UCX, they almost double injection rate just by switching to UCX with accelerated layer, and they show sub-micro latency with running MPH. It's actually with ConnectX 4, older generation of Mellanox interconnect. This slide I borrowed from our partners from Mellanox. They demonstrated UCX running on Azure Cloud with Star CCM application. It's probably Azure was running this. And it shows that running UCX in cloud, it's actually scales really well with UCX and HPX and accelerated collectives on top of UCX and so on. And there is pointer and slider to the Azure images with UCX that you can use to run this sort of workloads. Now it's also highlighted here their work on Nickel. Essentially, they replaces internet point-to-point communication layer in Nickel with UCX that leverages again accelerated capabilities of UCX. And Nickel library also will essentially benefit from internet communication using all optimizations we have. And I think here they have some performance numbers to share. There's a description of platform with V100 NVLink with 6 GPUs. They're running Nickel plugin, comparing the Nickel verbs, which is implementation with RDMA core, running collectives using UCX, so they demonstrate that they reach better bandwidth with better all reduced numbers by running UCX. This is another work, this research work by Stony Brook University. They used UCX, our thread safety capabilities. Essentially with UCX, you can allocate something called worker. They let you allocate network resources per thread. And once you have this resource allocated per thread, you don't, each thread essentially have the same set of isolation in terms of network abstraction as a process. So there's no really locking happens there and so on. And essentially lets you to get better performance with OpenSHMEM when it's running a threading mode. And here they demonstrate that essentially UCX with OpenSHMEM using this mode with workers per thread scales pretty much in the same way as you have separate processes. This is a slide from NVIDIA. As I mentioned, they did some great work on UCX Pi and Dusk, and essentially they highlight here the way they use UCX for their business needs, which includes AMPH OpenMPI, Parastation MPI, Rapids, and Dusk. This is their architecture of Dusk, Python, and Rapids. And essentially, you see UCX sitting on the side there, inside of the Dusk. The Rapids accesses power capabilities through Dusk, which is essentially task-based distributed runtime, and Dusk uses UCX Pi to communicate between jobs. And here's the highlight more ongoing work. Sorry, I jumped slides. Essentially, UCX Pi is still work in progress in terms of adding new features, optimizations, and so on. And some of the features we're focusing on right now, actually, improvement in our pipeline communications through GPU to host to UCX in cases when they cannot use GPU direct. Topology awareness, essentially providing UCX with knowledge how to select closest GPU to the NIC, and so on. And this is some of the highlights, how they use GPU HCI affinity, this work in progress, to highlight how it's important to select right affinity for GPU, CPU, and NIC. If you don't do it right, it will be very helpful for your performance. So as I mentioned, we work with ROCm GPUs as well. This slide, courtesy of Park Louis from AMD, one of the developers on UCX, and essentially they implemented ROCm transport on top of UCX. And similarly, so what is really nice there, they implemented relatively small plugin in UCX, and once you have plugin, they can use all the same top-layer algorithms that have been developed, let's say, for NVIDIA GPUs. They can be used for AMD. So it's really fantastic. With relatively small effort, they kind of leverage all the algorithmic work that has been done on protocols, and these two companies essentially share all this work, which has greatly saves development time. And it's how we manage in relatively short time, just like 1-2 releases, provide rocking GPU support on the same level like NVIDIA. It is some of the performance numbers for Intranode. Next slide from Intranode. The share pretty much showing that they're maxing out performance in latency of PCIe, and the same for Intranode communication. Essentially, you get close to native numbers what you can get with if you with PCIe and Knox InfiniBand or TCP and so on when you use both NVIDIA and AMD GPUs. And I believe UCX today it's only communication library that supports both NVIDIA and AMD GPUs pretty much on the same level. I'm not aware about of any other communication abstractions that have sort of this level of support for GPUs. This slide from Oscar Hernandez from Oak Ridge National Laboratory. They have been using UCX on various platforms like Summit Power 9. They have DGX2 cluster, which is a GPU dense system. They use it on Wombat, which is a ARM and NVIDIA GPUs cluster. And essentially, for them, it's the same network layers they use across multiple systems. And now they start to do more and more work in ML and AI space. They start to use Rapids, Dask, and all this layer for ML and AI. And what is really nice, the same level, the same optimization, the same level of optimizations that have been done for HPC and MPI also use exactly the same layer used for their AI workloads. And this is like a list of applications they run on NVIDIA plus ARM system, Wombat at OCF, which broad variety of applications. There's full report you can follow the link there for all the specific application results and configurations they used and so on. I'm getting to the end. We have like only 1 or 2 minutes left. 1 minute left. So I will probably finish this slide and I will pause for questions. So Char++, runtime environment, which is alternative to MPI, UPC, and so on. I think it's used by NAMD, if I remember correctly. Also has native support for UCX without going through MPI. And there's some slides I borrowed from CharWorks, Nitin from CharWorks. They show how it was integrated with UCX. And they demonstrated some fascinating improvement in performance by switching from MPI to UCX and leveraging semantics that we have there on their small system. Like 49% speed up with Changa and 32, 161% number jobs, increasing jobs that can execute using Char+ for Changa per day and so on. So very, very interesting. So I have more slides from Los Alamos, but we're running out of time. And I pause here for questions. Any questions? Now it's a good time to stop and ask.
Hello?
Yes.
Thanks for the talk. That was very interesting. So near the end, you said Charm++ has native support for UCX without having to go through MPI. Does that mean the general way to use UCX is to compile your MPI to use UCX and then just use that MPI for everything, basically?
Well, this is how MPI libraries use us. We have, as I mentioned, for example, Charm++, they have chosen to use UCX directly because we provide a bit broader semantics compared to MPI. For example, we have server-client semantics, we have active messages, we have streaming APIs that don't exist in MPI, but it's useful for other applications. Some of this we added for storage, some of this we added for AI workloads, and Charm++ ended up using some of these other APIs. And apparently it helps. And also, when you use directly, you don't have overheads of MPI. You have a lot of extra logic in MPI, like managing data types and so on, that we not necessarily have. So you can save some of the overheads, but I think most of the benefits, particularly Charm++ case, what you see, it's simply from using different semantics. And not necessarily from using, avoiding API. They just found in API and communication protocols that better fit their needs. And the same case we see with email in, for example, Rapids. They used to use MPI, and they switched to UCX, and they observe better performance. And part of the reason that we have, native support for GPUs. With MPI, you don't really have direct access for GPUs. It's all abstracted from you. With UCX, it's more exposed, more fine-grained, and they have better coupling between GPUs and interconnect. And this is how Rapids prefer to use UCX. Another key API that they use is server client. If you know MPI, you start the job, you have all the jobs running together, and you cannot really have server client with semantics with some process come in, joins, and disconnect. This is not entirely true, actually. MPI has an option to join different communicators and disconnect, but still it's very coupled as a job. With email and AI workloads, it's completely different. The same for Spark, actually. They have completely server client. You have a client potentially launching in other servers or separate servers running in another system, and they connect to server, disconnect to server, jobs going up and down and connect to another jobs. It's more really like server enterprise like software. And what they're really using from UCX a lot, it's actually our server client API and some parts of active streaming API for streaming data. So hopefully this answers your question.
Yes, thanks. Another question on that. So suppose you want to run an application that doesn't have native UCX support. Is the only way then to go through an MPI implementation?
Depends what is your application. If you're in classical HPC, yeah, MPI is de facto. And yes, please use MPI. This is the easiest way. If you're in email, AI space, you can use Rapids, Dask, Spark APIs. They have own abstractions. But for HPC workloads, yes, I would say MPI is probably the way to go. We have quite a few OpenSHMEM users, with again, it's biggest partition global address space programming models that use UCX. They don't use MPI. But in HPC space, typically we see that people access UCX through MPI or through something like OpenSHMEM.
Thank you.
Does that answer? Okay, great. I see you posted. I have few more minutes. They want. I have 2 more slides. I can spend time a little bit on this. So this slide from Los Alamos National Laboratory. And this slide came from Howard. He's maintainer of OpenMPI, and he actually provides some useful information here because sometimes it's challenging to coordinate, hey, what exactly version of OpenMPI I have to use with UCX, which has best integration and so on. And he's as a maintainer shared with us quite useful information. Hey, go with OpenMPI 4.02 or later. Use UCX 1.7, or I would advise now going why not 8. There's multiple improvements in Y-sided, better GPU support. So he kind of listed all the new features that he leverages. He mentioned PMIX. Actually, with great, this came up. So I don't know if you know it's PMIX, but MPI has this almost like third-party project for some MPIs, which launches the jobs and provides out-of-band channel to start jobs on large-scale machine. OpenMPI using something called PMIX and pitches Hydra. So the UCX doesn't provide this launch capabilities. It leverages whatever MPI uses to start the job. So pretty much for us, for UCX, MPI is responsible to start the job. We don't care what the way they do it, as long as they know how to do it and provide out-of-band channel to exchange, for example, the addresses to connect machines, we are fine. So OpenMPI uses PMIX, MPitch comes with Hydra, and there's updated embedded PMIX versions to use with OpenMPI that they recommend. There is 2 transports that use UCX and OpenMPI. One is BTL that use UCT. We had problem with this layer, and I think what he's saying, he does advise to use it. He also mentions that, hey, if you run with InfiniBand, there's embedded layer in OpenMPI called OpenABBTL. It has been deprecated. Don't use it. Make sure to use UCX instead of it. And the same goes for other layers like MXM and Sieves that used to provide some InfiniBand capabilities to say, hey, go with UCX. This is pretty much default transport now. He also shared some tunings that he is using on Summit Sierra, which is power system, that he found useful. He also, there is links to UCX wiki page that Howard updated with tunings for various GPUs, NVIDIA GPU, how to build ROC with UCX, and so on. And I believe this is truly the last slide that I have. So hopefully you learn more. I encourage you to, go and visit our GitHub, learn about the project. If you end up using for your cluster competition, don't hesitate to ask us, and questions on GitHub. We'll try to help you, or mailing list, whatever channel you prefer. We're here to help you. It's also a great research project. So if you're looking for a project to use for research work, or to hack around, or kick off your open source contribution, we are very friendly. We actually, in the last few years, we had quite a few students that have been using from Stony Brook, from UTK, that published papers using UCX and build projects on top of UCX from California University. So we actually had multiple research publications coming from students based on UCX. We also had some upstream, like active messages work, was contributed completely by students, which is based on his publication. Our new project, which based on Collective, it also very much was triggered by students from Jerusalem University that decided to upstream and contribute his project to open source. So this is kind of great opportunity to get exposed to open source. And I pause again, probably the last time for the questions.
I have another one. You on a slide 2 slides ago, it mentioned PMIX. What exactly is the role of PMIX in UCX or UCX OpenMPI?
Yeah, so PMIX has broader role in OpenMPI and other, like in actually OpenSHMEM as well. So if you have MPI API that you run MPI init, you do MPI run, right? And it starts your job, and you call MPI init, and magically you can talk to all the processes. So some of the magic that behind MPI run starts the job, it's pretty much PMIX, because there is tons of code in the project that's responsible for starting the processes on the 1,000 or 100,000 machines. It's actually very difficult, and there's quite a lot of research work was done there to enable startable jobs on these large distributed systems. For example, like 5 years ago when I was working with OpenMPI, to start it on our inaugural Jaguar system, this was just a little bit under 200,000 processes. It was taking 40 minutes to start the job. Like you run MPI run and you wait. PMIX project and Hydra as well spent a lot of time optimizing this launch time. So today you can start under a minute and probably 30 seconds on the same size of the system. And they're pretty much responsible for starting the jobs and providing out-of-band channels to propagate the errors to your nice errors that you see in MPI run when it fails. It's all done through PMIX or something like Hydra. UCX doesn't use it all. We don't link against PMIX at all. I just wanted to highlight that OpenMPI and other layers use PMIX to start the jobs. And when it started, they use PMIX to exchange information about UCX addresses between various machines. But again, we don't do it internally in UCX. It's completely done by MPI or Chan++ or any other runtime environment. Does it clarify a little bit?
Oh, yes, very much. Thank you.
Any more questions?
Is there a big difference between the OpenMPI and the MPI-CH implementations of UCX?
No, so what I saw, they get, because they use UCX, they actually get nearly identical performance for point-to-point communication. Now, if you look into collectives and GPU support, story will be a bit different. Because for now, we don't provide collectives. They implement on collectives algorithms. OpenMPI, for example, can use H-call or algorithms. I think the same true for MPICH. So you may see different performance in collectives, for example. You also, these libraries have different support, level of support for GPUs. I think as for now, if you run on GPU systems, NVIDIA or AMD GPUs, OpenMPI will have better support for GPU, which what it really means, it means support for GPU direct. Essentially, if you do MPI send receive and you pass pointer to the pointer to memories that resides in GPU, OpenMPI most likely to do a better job. I just was communicating with MPICH developers 2 days ago. They implementing something similar in MPICH, so you will have similar support for GPUs. I think they're just a little bit behind. They just came back to us asking for more and more features for GPUs. But I think this is going to be one of the differentiations that collectives and GPU support. My advice for your runs, once you're in competition, try both and see which one will give you best results.
Thank you.
But yeah, in some cases, actually, the difference can be in performance numbers can be quite significant. Any more questions?
Hi, Pavel. This is Ophir. Do you hear me?
Yes, I do.
So I will comment only, no questions. But first, recent Intel MPI, I think update 7 is has UCX embedded. So if you use Intel MPI 2018, that uses the DAPL transport under the Wi-Fi, and now they use UCX. So that's since few months, like half a year or so.
Really? Okay.
Yeah, update 7, they use UCX. Yeah.
Maybe we should highlight it somewhere, because I think most of the people that work on UCX not aware about this.
Yeah. That's one. Second, related to the Charm++ support. Charm++ added they have their lower API layers. They call it machine level. So they have one for MPI and one for UCX directly. So if you use the UCX, you can use it without MPI, but you still need to the PMIX library for spawning your MPI runs. So I added few. I was testing a few of those with Changa, so you can try to play around with it. You can try to install any MPI and just use the MPI machine layer, or use the UCX and use the UCX machine layer. So when you build the Charm, you select the machine layer that you want to build. If you use UCX within MPI or UCX within the UCX machine layer, you might see minor results, because they use both the same low-level engines. So it's up to you. I mean, you can try both, see what works better in the cluster. Okay.
Afir,
yes.
Yeah, very useful. Maybe you should post, your Charm++ instructions and Intel MPI instruction on read the docs.
Yes. Let's take it offline. We can. Yes.
Yeah.
So I will send you some links from, I think Intel already published some of their documentation, so we can do that. And I have some of that on the HPC Advisory Council wiki, so we can see if we can duplicate that or link to that or something later. Let's talk about that.
Yeah. Thank you.
Okay, so if there's no more questions, sorry for the delay on the time, and I want to thank Pavel for being with us, and use the OpenUCX questions if you want to ask them directly. You can use our Slack channel, and any more questions, we can try to help you. Okay. So I will post also the recording on the box, so you can, if some of your team members couldn't show up, they can look at that later on. Okay.
Thank you. Share it with me. Please share this with me because some people ask about recordings as well.
Yes, I will share. Okay. Okay. So thank you all for joining, and see you tomorrow for our GROMACS. Same time tomorrow. So I will send that links to you in the Slack. Okay.
Thank you very much, guys. Good luck in your competition.